Jump Game 7, you start at index 0 on a string of zeros and ones. Each jump moves forward by at least min jump and at most max jump, and you may only land on a 0. Example 1, from index 0 you can reach indices 2 or 3 in one jump. Index 2 is a 1 so you cannot stop there, index 3 is a 0. From 3, jump to 5, the last index, also a 0. So the answer is true. Example 2 uses the same jump limits on a longer string. From index 0 the only 0 you can reach in one jump is index 3. From 3 you must land on 5 or 6 next, but both are 1s, so you never reach the last index. The answer is false. Picture a reachable 0 as a flashlight fixed on the string. It paints a forward band of light. That band does not start at the very next index, it begins min jump steps ahead and runs through max jump. Only zeros standing in that lit band are within one legal jump. As you discover more reachable zeros, each one switches on its own beam. When two forward bands cover the same index, the light stacks there, one cell can sit under several flashlights at once. Other cells never get touched and stay dark. For the next 0 down the line, you do not replay every old flashlight. Look at the ground under that cell, is any beam lighting it? If yes, that 0 is reachable, and it immediately turns on its own forward band for the indices ahead. A single left-to-right pass can track that in constant time per index. In the full solution we will remember which indices are reachable in a DP array drawn under the string. Same picture on the usual example string 011010 with min jump 2 and max jump 3. From index 0 the forward beam lights indices 2 and 3 where the zeros are. Once you stand on index 3, a second beam reaches index 5, the last index. To implement the lit floor check without rescanning everything, slide a window over the possible jump sources behind you and keep a running count of reachable zeros inside it, update in constant time as you walk the string, one linear pass. Under the characters we keep a DP row, true where we can stand on a 0. Index 0 is reachable from the start, so we set DP of 0 to true and highlight its forward beam from min jump through max jump. Besides the DP array, we only need one integer coverage counting how many active beams touch our current position as we sweep. We sweep by left to right. At index 1 the entry test I greater than or equal to min jump is false, so no beam has started yet, coverage stays 0. At index min jump the entry test looks at DP at I minus min jump, that is DP at 0, which is true, so we increment coverage, that is beam entry. Then we write DP at 2, coverage is positive but S at 2 is a 1, so DP at 2 stays false. At index 3 the string is a 0 and coverage is still 1, so DP at 3 becomes true. That means this index will later contribute to coverage when we pass its beam start at 3 plus min jump. At index 4 the exit test I greater than max jump looks at DP at I minus max jump minus 1, that is DP at 0, which is true, so we decrement coverage, beam exit. Coverage is now 0. The character is a 1, so DP at 4 stays false. At index 5 the entry test sees DP at 3 is true, so we increment coverage again. The last cell is a 0 and coverage is positive, so DP at 5 becomes true. Every loop pass applies the same two checks, increment on beam entry using I minus min jump, decrement on beam exit using I minus max jump minus 1, then set DP from coverage and S. Let n be the length of S, time is linear, a single scan from left to right, and each index only triggers a constant number of updates to the sliding coverage count. Space is order n for the DP booleans that remember which indices are reachable, beyond that we only keep one integer for coverage and the loop index. Pseudocode for Jump Game 7. Function canReach takes the binary string s and min jump and max jump. Let n be the length of S. If the last character is not 0, we can never land there. Return false immediately. Allocate a Boolean array dp of length n, initially all false. The start is reachable only if the first character is a 0. Initialize the sliding coverage count to 0. Loop I from 1 through n-1. If we have reached min jump distance from a reachable index, that index's beam starts covering us. Increment the coverage count. If we are past max jump from an old reachable index, its beam no longer reaches us. Decrement the coverage count. Mark dp at I true only when coverage is positive and s at I is a 0. Return whether the last index is reachable.